So before going to start our session, I will just firstly introduce myself. So this is Vijay Rane. I'm a Prime Minister Research Fellow in the IIT Delhi, and particularly I'm involved in the IITD UQ, IIT Delhi and University of Queensland joint PhD program called UQIDAR. And currently I am here in the Brisbane, in the Center of Orthophotonics and Electronics, working on the optoelectronics device fabrication and its characterization. So today we are here to discuss about the course, the stereochemistry, which is offered on the NPTEL, and the course is taught by the Professor Amit Basak. He's from IIT Kharagpur, as you know. And particularly, these are some topics that we have covered in the first, second, and third week, as well as fourth and fifth week in this course. And today we'll particularly focus on the confirmation of the cyclohexane, particularly substituted cyclohexane, and their stability and that kind of uh, factor we'll see in the today's problem. So before going to problem, is anyone have any doubt regarding any topic previously whichever covered till in the course? So if you have doubt, please drop it in comment session so as I can we can clear that doubt. So this is the first question. So please let me interrupt in between if you have any doubt. So this is the first question, and the question is: in which of the following compound the tertiary butyl group is most likely to occupy the axial position? So they have given the four different structure of the compounds, and we have to just select the most stable conformation in which the conformation in which the third butyl group, that is C. As you know, this third butyl group is highly bulky, so it always try to occupy in the equatorial position in the cyclohexane. But in some cases, there are some possibility it will occupy the axial position as well. So we'll draw the first one by one this conformation in the form of chair. So let me draw first on the structures. So first structure is like this, right? So in this one, let us draw first this one, and this is directed downward. So this is directing downward methyl group, and this is third butyl group C Me3, right? All right. So this is the this is structure of the compound, and this compound can be flipped into the another form, right? So by just ring clipping. So let's say if you perform the ring clipping on this compound, so in this one, this third butyl group will go to the equatorial position, and here the methyl group will be in the equatorial position. So this is the stable conformation in this one. So in this one, the third butyl group mostly, oh sorry, I just made here mistake. The CH3 here, right? Because if you do the ring flipping, so this methyl group will be first it is axial. That was correct, I think. First it is axial, and then now it will be converted to equatorial, right? So after ring flipping, the axial bond converted into the equatorial, and vice versa, equatorial bond convert into the axial. So this material, this compound will exist in the form of this one. So this is the structure of this compound. We have just did the ring flipping operation. Uh, we have just performed the ring flipping on this. So most likely this compound stay in this form, and we can draw the arrow, distinguish it by the size of the arrow. So the equilibrium of this ring flipping will be the towards the most stable form. Let's draw the second compound. So in this one, this is structure and this directed downward. So we'll draw it in the equatorial position so as it will be in the downward form. And this methyl group also directed downward. Let's say this is the one. And there are two oxygens atom in the contained in the ring. So these are the oxygen atom. So see, in this structure, what will happen? The uh, here in the first structure, there are fair chances of 1,3-diaxial interaction, right, with this third butyl group. And this third butyl group is highly bulky, so always try to stay in the equatorial form. So that's why this ring flipping will take place. But in the second structure, if you see, this third butyl group already in the equatorial position, and this methyl group is in the form of axial position. And if you see, here there are no hydrogen atoms, there are only lone pairs. So there are some kind of less chances of the ring flipping here. So after ring flipping, which structure we will get here? So let's perform the ring flipping on this molecule. So if you do the ring flipping on this one, so we'll get a structure in which the now I did ring flippings, right? So this equatorial bond, now it converted into the axial, right? So this CMe3, now it's an axial. Here there are two oxygen, and this methyl group converted into the equatorial because it was in the axial form. So this is the CH3 methyl group. So this is the structure of this one. But here, if you see the which structure is stable, in this one, this third butyl group is in the axial form, so it will not a stable structure. So the equilibrium in the ring flipping, particularly for this molecule, will be in the side of this one. So let's say, let me draw this correctly. So like this, right? So majority of the material will be in the present in the form. So this is the stable. Here it is, this one is the stable. And let's draw the, this is the A, this is B. Let's draw now C compound. And if you see the C compound, let me draw here. All right. So here there are two oxygens are present, and one third butyl group directed downward, right? So this is the third butyl group, and this methyl group directed is also directed downward. This is also methyl group, and in this one you can see here. So here, if you do the ring flipping here on this molecule, so after ring flipping, what we will get? We'll get a structure like this, and in this one, third butyl is at the uh, axial position, and this methyl group is on the equatorial position. So this is the structure. So in this one, third butyl group is at the axial position. And if you see the 1,3-diaxial interaction between here, so here there is oxygen is present, so there is no 1,3-diaxial interaction like this. But if there are some CH, if it is present, the CH hydrogen bond is present, then that time we face the we encounter the 1,3-diaxial interaction. So in this one, there is no such 1,3-diaxial interaction. So that's why this particularly this C molecule present in this form. So equilibrium, if I draw the equilibrium of the ring flipping, so how it will be? It will be in this fashion, right? So this is the major form, and this one is the minor form. And similarly for the D structure, I will write in the another slide. So let me check the structure. What is the structure? So it's like a like, so this is the D structure, and if I draw the structure D in this one, the third butyl group present downside and methyl also in the downside. So let's draw butyl group and methyl group facing downside, and there are the oxygens which is set to the two, right? So one, two. It's not directly attached, it's attached. So here there is one oxygen and the another oxygen here. So this is not third, this is methyl group. And if you perform the ring flipping on this one, so how it will be? The structure will look like this. So the third butyl group goes to the axial position. The oxygens are here and the methyl group will be equatorial position, right? So in this one, if you see here, the third butyl group is at axial, but if you see there are this theory hydrogen is present at one side. So here there is fair chances of the 1,3 diaxial interaction between the terbutyl group and the hydrogen. So here this structure is the stable one. So if you see the all the structure, what we can see in the C structure here, we can see the terbutyl present in the axial position, which is major conformation or the most stable conformation among these two. So the option C is the correct option for this one. So hope you got the answer for this one. So if you have any doubt, please let me know in the comment section. If you don't have, we'll move for the next question. All right. So here I will also upload the PPT for with the some explanation. So you can have a look. So this is the second question, and in this one, which of the following compound exists in the twist boat conformation in the most stable form? So first of all, we'll see one by one. So in this one, so this conformation is of course will not stay in the twist boat form because uh, if you flip the structure, let's say if I draw the structure and the hydroxy group at the axial position and one at the equatorial position, right? So if you flip the structure, so the hydroxy group will go to here equatorial position and here it will go to the, now it will go to the axial position, right? Because after ring flipping, axial bond converted into the equatorial and equatorial bond converted to the axial position. So like this. So these compounds present in this form both have the equal stability. So obviously this is not the option. If you see the second structure, it has one third butyl group. Let's draw this. And one third butyl group is at the equatorial and one at the axial position, right? Similarly, in the second one, here we can see the one third butyl is axial, second is at the equatorial. If you do the ring flipping on this third compound, so both one will go to the equatorial, both will go to the equatorial here. And the fourth option, fourth compound, if you do the ring flipping, then what will happen? So the structure of the material or the compound looks like this. So this double bond will be here and this equatorial will now convert it into the axial one, right? Which has the uh, isopropyl as a uh, substrate, right? Which is at the second position, right? Like this. It's not the backside carbon, it's on the front carbon. So ignore that one. So like this one. So which conformation exists in the twist boat? So the first one option is obviously neglected in this and the this option also neglected because if you see it is third generally most of the compound which has the third butyl group, they can only they try to stay in the twist boat form. And if you see the structure, this one, So if you try to flip this structure, this compound, let us flip this one. So here, this third butyl group will go to the axial one, and this will go to the equatorial. So if you, although if you try to flip the compound B, we'll get the conformation which has the one, at least one T-butyl group. That means if the ring flipping will not help. But if you see the C structure, after ring flipping, what will happen? The both axial tert-butyl group get converted into the equatorial tert-butyl group. So this material, this compound will not stay in the twist boat form. So the B option is the correct option, because if you, although if you try to get stabilize the structure by using the ring flipping, we still encounter one, at least one axial group here, axial tert-butyl. So that's why this compound try to convert it into the twist boat form to stabilize the structure of itself. So the option B here is the correct option here. If you see the here, the twist boat structure will be looks like this. So you have a, please have a look at the structure, and in the twist boat, try to minimize because hydrogens are present here, so they will not encounter much interaction. And the tert-butyl, bulky tert-butyl is stay away from the here the inner side of the boat. So that's why this is the stable conformation for 1,4 ditert-butyl, cis-1,4 ditert-butyl, right? This is the, so this is the structure of cis-1,4 ditert-butyl cyclohexane, and which is always stay in the form of twist boat form to stabilize the structure. The next question, if you have any doubt, please let me interrupt in between, or just put the comment in the chat box. So the next question is, which of the statement is correct regarding Z2-methyl cyclohexyl dilidine acetic acid? So this is the structure of the compound, and which statement is correct? So first of all, before going to the statements, we'll convert the structure in the form of the chair. So if you have any kind of alkene substituent, always try to draw the structure in which the alkyl substituent at the tip of the boat. Let's say like this. You can draw in this fashion, or else what you can do, you can draw in this fashion, because it is easy to understand the here like this. So here there is C double bond O to H, right? And here there is one methyl group as well as one hydrogen. So not sure which position is the correct for this. So we'll draw both available position here. So in first option, the hydrogen will be the axial and the methyl group at the equatorial. And in second possible structure, we'll draw the hydrogen at the equatorial and the methyl group at the axial position, right? So these are the two possible structures present for this molecule, because they have not given the exact stereochemistry of this hydrogen. And the first statement is, in the most stable form, it has axial methyl group due to the existence of A13 strain in the equatorial position. So the first option, first of all, we need to understand which is more stable structure in these two. So let's say I will give the numbering label A and the B. So does anyone let in the comment box? So which is the most stable structure for these two? All right. If you don't have any, comment, let me go for the structures. So if you see this structure carefully, so here the methyl group is at the equatorial position. But if you look at the structure of this one, this bond is cis, right? So this bulky acid group and this methyl groups make a 1,3 strain, right? A 1,3 strain. So A13 strain is present in this molecule. But if you see the structure B, here there is hydrogen, which is less bulky as compared to methyl group, right? So here the A13 strain is less. Here A13 strain is less as compared to the structure A. So that's why so structure B is the more stable structure here. And if you look at the statement, in the most stable form has the methyl group at axial, right? Up to here it is correct due to existence of A13 strain, right? So in this one, the methyl group, why this methyl group takes the position axial position because of 13 strain. So that's why the methyl group is at axial in this structure, and the statement is also correct up to here. So because of its A3 strain in the equatorial position, right? So if you look at the equatorial position, it has more A3 strain as compared to the structure B. So that's why the methyl group is at axial position, and this is the more stable structure. So the option A is the correct option. So we can also look for the other option. So in the most stable form, it has methyl group equatorial. So this is wrong. Methyl group as axial position. The third option is the most stable form, methyl group due to existence of A12 strain. No, this is A13 strain. So this is the wrong. And the last option, in the most stable form, it has equatorial methyl group. Obviously, it is wrong because the methyl group is at the axial position. So the option A is the correct option here. So here is the solution. You can have a look after that. We'll go for the next question. Consider the trans 2-isopropyl 5-methyl cyclohexane. So this is a structure. Its common name is methionine. And if you try to convert this, first of all, if you see in the stereochemistry, if you saw the structure, first of all, convert the structure in the form of chair or in the, this is the 2D form, right? So try to convert into the 3D form. So as you can get the more better understanding of the question. So first of all, we will convert the structure in the 2D form, sorry, 3D form. So this is the structure and it has one keto group. So this keto group will write like this. It has the CHMe3 and which is directing upward. So which is directing upward here, CHMe2, and it also have the methyl group which is directing downward. So methyl group at, let's give the numbering 1, 2, 3, 4, 5, and 6. So which is at the 5 number carbon. So this is the 1, this is 2, 3, 4, and this one is the 5, and it has the methyl group directing downward. So let's say it's directing downward, right? So here both are the at equatorial position. So the correct statement we have to identify. So we'll go for one by one. In most stable form, all right. So here the question of stability. So we have to do the ring flipping. Always such question, always try to understand question first, and in case of stability type of question, in particularly the cyclohexane system, we have to convert the structure in the we have to do the ring flipping always. So if you do the ring flipping, just pull this ketone group downward, so it will be like this one, right? So the keto group directing downward, and this equatorial group now it converted into the axial. Always note, after ring flipping, axial group converted into the equatorial. So it's always keep note, axial converted equatorial and vice versa. If it is equatorial, then it will convert into the axial. So you can note this one. So here, this now it converted into the axial position, and this methyl was the equatorial. Now the methyl will convert it into the axial position. I will draw here. This is the methyl group, right? So this is the structure. These are the two structures of this compound, and which is stable structure here. So if you look at the structures, here it is equatorial. So here there definitely the, as we have seen in the previous 1,3 strain present, right? The previous question also the regarding the same. So here also here we have seen there is some sort of 1,3 strain is present. So that's why this structure is less stable and this structure is more stable, right? So here also the same scenario. So if you draw the structure, in this structure is less stable. And let me give the numbering. This is the A structure, this is the B structure. So this B structure is more stable, right here. But but if you look at this one, here the methyl groups lie at the are at the axial position. This also you have to take into consider. So we'll go for one by one option. In the more stable structure, it has methyl group has axial position due to 1,3 diketo effect. Here there is 1,3 diketo effect present because the keto group also this also the correct option, right? Up to here it is the correct statement. And isopropyl group present at the equatorial position. But if you see here, the this statement is also itself it's incorrect one, because in if you see the structure, if it is methyl group, you draw the axial position and isopropyl at equatorial position, it doesn't satisfy the structure, right? Because if the methyl group axial, then it should be axial, because if we have performed the rim clipping and we have see in the structure that I have shown here, these groups both are equatorial, and in the flip structure both are the axial position. So this statement is incorrect. The second statement is, in the most stable form, it has axial isopropyl group due to 2-alkyl keto effect and equatorial methyl group. So here also both are axial equatorial. These both are incorrect one, because both should be axial or the both should be equatorial, because we have converted the structure. So after converting, we get the structure, right? The statement C is, in the most stable form, it has equatorial isopropyl group, all right, and methyl group, all right. So equatorial axial methyl group, you avoid 1,3 steric 1,3 syn diaxial strain. So if you see here, up to here it is okay, but to avoid 1,3 strain, it's not able to avoid, right? Here if you see, if it is attain the both group attain the equatorial conformation, then it encounter the 1,3 strain. So this is also the incorrect statement. The last statement is, in the most stable form, it has axial isopropyl group, all right, and axial methyl group, all right, due to the combination of 2 dialkyl keto effect and 3 alkyl keto effect, right? So to avoid the 1,3 strain, it attained the axial conformation, right? So, and this is the more stable conformation. So the statement D is the correct option here. So here, what are the factors that we have to consider? The 1,3 A13 strain. So this is the major factor here because this, if you see the bulkiness of the group, it is highly bulky group as compared to the normal hydrogen or methyl. So this compound always try to convert into the more stable form. Although there are some 1,3 diaxial interactions are also present because of these groups are attaining the axial position. But still, because of this strain is very high, 1,3 strain, so the compound try to stay in this form in which the methyl as well as the isopropyl group is at the axial position. So the statement D is the correct option, correct statement here. We'll go for the last question or few, we'll take some question, 2 or 3 questions maximum, and then we'll discuss general questions. So this is the one question and it's based on the acidity concepts. So these are the 4 structure they have given, or the two pair of the structure they have given, and we have to identify the structure. So before going to the structure, first of all, I will like to note here. So for higher acidity, we should have less pK. That is, if the compound has the less pK value, that it means it is highly acidic. Also, aziness, availability of proton. So in the structure which has easily available proton, which is highly acidic. So we'll consider one by one structure here now. We'll just introduce one more slide. Right. So these are the 4 structures are possible. And if we look at one by one structure, let me draw the pair A with the red one. And let me convert this firstly in the chair form. All right. So these are the 2 structures, right? So first structure, this carboxyl acid group is directing upward. All right. COO minus. The next one directing downward, COOH. And this one directing upward. This is the third butyl group, right? So let me elaborate this group. So this is the third butyl group, right? So this is the bulky group. It has 3 methyl groups here. And the second structure also, this COH directing downward, CO minus, this one directing upward, and the third butyl group directing upward here, right? This is the pair structure 1, this is structure 2. So what you can see in the structure 1 and 2, this COH group is directing, is at the axial position, both COH axial position. In this second structure, both are at the equatorial position. So let's say if you do the ring flipping on this one, what we'll get? So obviously this structure we get is less stable because this third butyl group will go then the axial position. So no need to do ring flipping here. Because now we are in the situation, we can easily identify which structure is stable. So let's say here it is directing upward, that is equatorial position, right here, as we have converted. If you convert the structure by the ring flipping, if you do the ring flipping, then the tert-butyl will goes to the axial position. So which is definitely not stable, right? So here also after ring flipping, it will go to the axial position. So definitely these are the structures are the stable structure in this one. And if you try to check the, all right, first of all, we will convert the next as well. So next structure is how it will be. This is the trans. Here also it is a trans structure, right? So we'll draw the trans Deccan system. So this is the structure, and this NH3 plus will represent axial. This is downward, right? So this is the structure for the third one, and for fourth one. So this is the structure for the fourth molecule, right? And OMe will be at the directing downward. So 1, 2, 1, 2, here OMe is directing downward, right? These are the structure possibles. And here, if you see this, now we'll look at the what are the statements. So we have to identify the correct statement, right? So now we have converted all the structure in the chair form. All right, so we'll go by one. So in a pair A, it is having lower pKa than the 2. One has low pKa than 2. We'll check whether it is correct or not. So let's say 1 and 2. One has lower pKa value. It is definitely wrong, because if you see the pKa value, it has lower pKa. Why? Sorry, it has higher pKa. Sorry, I did mistake. It should be like this. If you check the pKa, so pKa for this one will be higher. Why? Because if you see there, if you expand this COOH group, let me expand it. So I will draw it the different color. All right. So if I expand this one, here there is OH, right? And here double bond O. Here also C, double bond O, and O negative. So this O negative form the hydrogen bonding. What we call, this is called intramolecular hydrogen bonding. So because of this intramolecular hydrogen bonding, this hydrogen is not easily available for donation. But if you see the structure, these COH group are far away from each other. So they are very far from each other. So such intramolecular hydrogen bonding is not present. So that's why pKa for this one is less as compared to this structure. So we'll see the option. The A has lower pKa than B. Up to here it is correct. And in the pair B, the 3 have lower pKa as compared to 4. So 3 and 4, if you compare 3 and 4, let us say it has the NH3. And does it have any other substrate? Oh, all right. Here there is one substrate that we have missed. So here there is OMe, right? Set here. And here OMe is here. So if you see here, here also same possibility. If you expand the structure, let me expand here, and this N, it has hydrogen, right? Here there is fair chances of intramolecular hydrogen bonding. So these hydrogens are also not easily available for donation. So here this has pK less, that is more acidic, right? So the structure 4 and structure 2 are, sorry, structure 4 and structure 1 are more acidic. So we'll check one by one option. So in this option, what they have seen, structure 3 has lower pK than 4. This is the incorrect one, because we have seen structure 1 and structure 4 are more acidic. right? So this is more acidic, and here also 3 and 4. So this is more acidic and this one more, right? So the option A is the wrong, because what they have seen, the structure 3 has lower pK. This is obviously incorrect one. Then option B is in pair A, 2 having lower pK value. This is wrong, because we have already seen that 2 has the higher pK here. In the option C, the pair A, in pair A, pair A structure A1 has the lower pK than 2. All right, up to here it is correct. And in this pair B, 4 having lower pK than the B. All right, so the option C is the correct option here. So all right, so hope you are understand what they are willing to ask. So we just need to identify correct statement. So whenever we see this such type of question, first of all, first step is to convert the structure in the form of chair. Always for such cyclohexane systems, in many exams we have faced such question. We have seen some such questions. So the keynote for here is the just convert the structure in the form of chair form. Then you can easily visualize this what they want to ask. So here you can easily solve this question, right? So if you have any doubt, please let me know. All right, we'll move for the next question. So here is the some sort of explanation that we have provided. So please have a look here. And the next question is, we'll take this last question. In which of the following statement is correct regarding cyclohexane 1,2-diol? First of all, we'll draw the structure of cyclohexane 1,2-diol. This is cyclohexane and 1OH, 2OH, right? Cyclohexane 1,2-diol. The dipole moment of cis diastereomer is less than the trans. All right. So this is the structure in the 2D form, right? So we have to convert the structure in the form of chair. So first of all, I will convert the structure in the chair form. So this is the one structure. And if I do the ring flipping, so it will be like this, right? So the cis diastereomer is less stable as compared to trans. All right. So we have to draw the cis and trans, right? So let's say if I draw the cis isomer 1, 2, right? So this is the cis, and let me draw the trans isomer here. Right. So this is the trans isomer, right? And here, just for understanding, I will just immediately do the ring flipping. So here it will be OH here, the OH here, and here it will be OH directing upward, and here OH directing downward. So it doesn't matter which form we are writing here. So we'll consider only the one one isomer, sorry, one structure from this one, right? So the cis diastereomer is less stable than the trans. Less cis, the dipole moment for cis isomer, right? Dipole moment. All right. So the dipole moment, like whichever the polar group, let's say here, C, X bond. So if it is electronegative, highly electronegative, so dipole moment will be like in this direction for this bond. Let's say if it is hydrogen, sorry, chlorine, fluorine, iodine, or oxygen, nitrogen. In this case, the dipole moment directed in this fashion. So that we have to note. So the electronegative atom, the dipole moment for this bond is like this. So in this direction. So particularly for this one also, the for this bond it is upward. For this bond it is this side, right? Let me draw it with the different color. So in this direction, the dipole moment And in this one also, here and here, the average of this such direction, probably in the line and vector, probably we have seen in the class 9th or 10th, it is averaging, right? So let's say direction vector is in this direction. There are two direction vectors. The average of these two direction vectors will be, let's say it is perpendicular to each other. The average for the average direction vector for this one will be the 45-degree, like this, that we have to note. If you have any direction vector like it directing this way and second directing this way, the average direction vector will be the 0, because there is no dipole moment for this, because both vectors cancel each other. The condition is both vector have the same magnitude. Let's say it has x magnitude, it has the y, and let's say the y is greater than x and y are equal. So the overall dipole moment for this one is the 0. So here the average direction will be in this fashion. Just roughly that I'm just directing in this session. For this one also, let's say in this direction. So it has some dipole moment. But if you see the trans structure, the direction vector for this one is for this OH will be directing upward. For this one directing downward. So it has the 0 dipole moment. And here it is directing, let's say this side, and it is directing its side. It has somewhat, but if we compare these two molecules, the cis has the more higher dipole moment, right? And what they have seen, cis has lesser dipole moment. So this is the wrong option. Always here, for the question of the dipole moment, always there are in general trans has the less dipole moment as compared to cis. If the both groups are the same, if both group are different, it might be a different case. All right. So the next option is, so the option A is the obviously incorrect one. The next option is the intramolecular hydrogen bonding is stronger in trans. So intramolecular hydrogen bonding. So obviously it is not at all stronger. If you see this trans isomer, the OH groups are far away from each other. So obviously this is the incorrect option. But if you see this cis isomer, let me just expand the structure. All right. So this may present like this, right? And here there is fair chances of hydrogen bonding, right? In the cis isomer. Similarly for this uh, another ring flipped structure as well. I will draw that. So it has fair chances of hydrogen bonding. So obviously trans has the less hydrogen bonding as compared to cis. And but what they have seen, they said the hydrogen bonding is stronger in trans isomer. So this is the incorrect one, obvious, right? The third option is cis diastereomer predominantly exist in the boat form. This is obviously the wrong, because why there should be a reason why it should be stay in the boat form, because they're already stable, right? One hydroxy group, one is although present in the axial, but still there is, these are the hydrogens, right? So there is very less 1,3 diaxial interaction. So 1,3 diaxial interaction is very less, so that's why there is it will not convert into the boat form. So this is also the wrong option. And the D option is the IR spectra. The IR spectra, in the IR spectra, the cis diastereomer show the lower OH stretching frequency than the trans diastereomer. All right, so here there is good concept we can see here. So IR spectra, let's say there are some different kind of molecules. Let me draw in this fashion. There is OH. Let's say here also O, and here hydrogen is there. All right. So if So this we have to consider. So if there are uh, intramolecular hydrogen bonding is present, the IR stretching frequency will be less. So this is the, you can keep note here. So for this question or for any other question, uh, you have to, you should know the effect of intramolecular hydrogen bonding on the IR stretching frequency. So the option here they give given is correct option, because cis diastereomer there is hydrogen bonding is present, as we have already seen here, and that's why the OH stretching frequency, it shows the lower OH stretching frequency than the trans isomer. Why lower stretching frequency? Because it has the intramolecular hydrogen bonding. The trans isomer, it doesn't have the intramolecular hydrogen bonding. That's why it has the higher stretching frequency. So that's why the option D is the correct option here. All right. So does anyone have any doubt here up to here? This we can see the also give the explanation in this form. We can convert the structure in the form of the, what we can say, Newman projection formulas, and then we can get the answers for this one. Yes, if you see the trans isomer, there is one form here, right? So it has somewhat dipole moment. So as we have seen for IR active molecule, there should be a dipole moment, right? For IR active molecule, this is the condition for IR active molecule. So why the C double bond O, uh, or let's say H X. So it has somewhat dipole moment. So this bond is IR active. And if you see the structure of the trans isomer, although one form doesn't have the dipole moment, let's me draw here structure, 1,2 form, let's say here. So this one, if I just rub all this, so here the direction of the dipole moment here is hit this direction. So the overall dipole moment is the mu is 0. But there are fair chances of this molecule to present in this form. So this is the more stable, right? And here both are nearly equal. So if you draw the equilibrium of this ring flipping, how it will be? It will be in the form of like this. So this is the form in which this trans isomer is majorly present. And so the dipole moment for this one, if you see the dipole moment, let me just show here. If you see the dipole moment, so this is directing to this side and this is directing to this side. So they are not 180, right? If you see they are, if it is directing exactly opposite, then it may cancel each other. But here they are not 180. There should be a somewhat non-zero dipole moment. So that's why it is IR active. So the good question. So this also we have to keep noted which molecule is IR active, which molecule are not IR active. And here also you can see here. So after ring flipping, I think these are the cis and this is this trans isomer. And if you see here in the Newman projection formula, here it has the hydrogen bonding, right? So if I just rub this hydrogen from here and draw hydrogen here, so it has here hydrogen bonding is present. In the same ring flip structure also, let's say O, it also has the hydrogen bonding. So that's why it has hydrogen bonding, and net zero dipole moment direction of the dipole moment will be in this direction, right? Here also in this direction. Let me draw the different. In this direction. So like this it will be. And in the trans isomer, how it will be? So here in one form, it is non-zero, sorry, it is zero, right? Because why it is zero? Uh, it is directing upward, and this, because of this, it's directing downward. So it has zero dipole moment. But if you see this structure, it has somewhat dipole moment right here. So it is non-zero dipole moment. This is also non-zero. So these three form are IR active. This is not IR active. If you consider only the OH, because overall it molecule has the somewhat dipole moment. If you see the overall molecule, so overall dipole moment, if you see, it has somewhat overall dipole moment because this remaining part, it's, and these two have these two carbon which has the hydroxy group, it has somewhat overall sorry, dipole moment. It has non-zero dipole moment because of this overall, if you look at the overall group. But if you consider only the two hydrogens, only the two carbon, so it has the overall dipole moment zero. Sorry, yeah. But if you see the entire molecule, then obviously it will have the somewhat dipole moment, right? So this is the question. So should we move for next some question? These are the some very, I mean, some sort of informative type of question. I will upload this PPT in the my Google Drive, so you can have a look for this question. So there are some 2, 3 simple questions are there. So this you can solve. I mean by yourself. Hope. I'll just stop recording. If you have any doubt, please let me know.